So we introduced the idea of Maxwell's equations, and then we kind of talked about them and said that they lead to other things. The biggest thing we saw that Maxwell did was he inserted the idea of displacement current into the idea of Ampere's law. And so what we want to do is sort of transition from chapter 32 to chapter 33. And we do that through Maxwell's equations. So if you remember Maxwell's equations, integral E dot dA equals enclosed charge over epsilon naught, integral B dot dA equals 0. It means there's no magnetic monopoles. Integral of E dot ds. Now that's going to be the induced EMF. Okay, that's the rate of change of magnetic flux. And then integral B dot ds equals mu naught I plus mu naught epsilon naught rate of change of electric flux. Now that's in general, but what about in a vacuum? In a vacuum, there's no enclosed charge and no current. So in a vacuum, Maxwell's equations look. In a vacuum, Maxwell's equations, E dot dA is 0 because there's actually no charge. Integral B dot dA is still 0. Integral E dot ds still going to be minus the rate of change of magnetic flux, and integral B dot ds, since there's no charge, is going to be just equal to mu naught epsilon naught rate of change of electric flux. So this gives us our new idea here of what's going on. Well, let's consider then, let's consider a situation in which we are looking at changing electric and magnetic fields. Okay, so the fields being produced, imagine like a wire with AC current. So that means the magnetic field near the wire keeps changing. And so we can imagine, in 3 dimensions. Okay, so in 3 dimensions we have X, we have Y, we have Z. Okay, now look in the XY plane. Imagine that we've got a magnetic field or an electric field. Let's say we have an electric field like that. Okay, and let's say that we have a magnetic field this way. Okay, so let's imagine if we did an integral up here. Okay, we did an integral for something like that. Okay, now so there's a magnetic flux through here. So this is in the XY plane. So in the XY plane, we have magnetic flux through that loop right there. So we're going to say this is some like delta X like this, and it's some height L like that. And so the integral E dot ds is minus the rate of the change of the magnetic flux. So integral E dot ds is going to be basically 0 across the top and the bottom. So on the right-hand side, this is going to be equal to E at x plus delta x, okay, times L. And on the other side, it's in the other direction because we're integrating down this way. So we're integrating around like that. So we're integrating up over here, so that makes this positive. Integrate down here, that makes the next term negative. So that would be minus E at x times L. Okay. And so that's going to be equal to the rate of change of the magnetic flux. The magnetic flux is going to be B times L delta x. Okay. Well, we look at that and we say, well, wait a minute, that's the L's will all cancel, And so then what we have is the delta x doesn't change, so this is going to be delta x times dB dt. And so we can rewrite e at x plus delta x minus e at x, bring the delta x over from the other side of the equation, and so that's going to be equal to minus dB dt. If we take a limit as delta x goes to 0, the term on the left over there, well, that's a derivative. So that means dE dx minus dB dt. Well, really, we realize that x and b are actually both dependent on both x and t. So really we should say the partial derivative of e with respect to x equals minus the partial derivative with respect to t. So hold on to that. Okay. Back to the original diagram, we also realize, okay, we have the y-axis here, okay, the x-axis, and then the z-axis was off this way. And we said, okay, we got an electric field is this way, and in magnetic field this way. Well, if we look at our other integral b dot ds equals mu naught epsilon naught rate of change of electric flux. Okay, so if we integrate this, okay, and we want to make a positive, so we integrate this way, so that would give us positive flux. And so that would mean that we have B times L, so this is some L this way and some delta X, B times L, B at X times L, minus B at X plus delta X times L. Okay, that's equal to mu naught epsilon naught times the derivative of respect to time of E times delta x times L. So like before, the L's are all constants, so they cancel. Delta x is constant, so it comes out of the integral. Then we can divide through both sides. So what we have is minus b at x plus delta x minus b at x. So all divided by delta x equals mu naught epsilon naught derivative of e with respect to time. Take a limit as delta x goes to 0. Once again, we have minus, again, these are really partial derivatives, partial b with respect to x equals mu naught epsilon naught partial of e with respect to time. Okay. So now what we've got here is we've got interesting derivative. I'm going to make that one positive and this negative over here just because I don't like having negatives to start an equation. So what we can do is look at the original equation. Okay, the one I told you to keep in the back of your mind. Partial of e respect to time equals minus partial b respect to partial of e respect to x, partial e. So what if we take a derivative both sides with respect to x? So this would be second derivative with respect to x equals minus partial respect to x of partial b respect to time. Well, we know that from differential calculus, the order of the derivative doesn't matter, so there would be partial respect to time of dB dx. But we already just saw that dB dx, okay, is minus mu naught epsilon naught partial of e respect to x, respect to time rather. So if I plug that in, we have the second derivative of e respect to x squared equals mu naught epsilon second derivative of e respect to time squared. Okay, so Well, that's interesting. So so this second derivative here is proportionate to that second derivative, and the proportionality is mu naught epsilon naught. Well, let's look at the other equation. So the other equation here, partial of b with respect to x equals minus mu naught epsilon naught partial of e respect to time. Now do the same thing. Take the second derivative here. So take another derivative. Again, the order of the derivatives doesn't matter. So this could be respect to x. But we know that partial of e respect to x is minus partial of b respect to time. So that means partial of b, second partial respect to b squared equals mu naught epsilon naught second derivative, partial derivative with respect to time squared. So they both have the same relationship with the same term. Now remember from physics 1, second derivative of y with respect to x squared was equal to minus 1 over v squared second derivative of y respect to time squared. This defined a wave equation. It meant that y was some y naught sine omega t plus kx, plus or minus kx. So this defined a wave, and so the speed of the wave was that. Well, if you look at what we just had, that means that we can then say that b and e are now waves. So b is some b naught sine omega t plus or minus kx, and e is some e naught sine omega t plus or minus kx, and the velocity, the speed is, or the velocity is going to be equal to, the velocity is equal to 1 over square root mu naught epsilon naught. Well, if you plug in what terms we know for mu naught and epsilon naught, what you get is the speed of light. So this is where Maxwell's equations really come in, because they are helping define what is light. Light is a wave. For a long time, Newton and Huygens' ideas were debated in physics. Most people went with Newton, who thought light was a particle, and then Maxwell does this. This is what makes Maxwell's equations, even though he didn't come up with any of them, is that he did this, and this determines that light is in fact a wave. So now we have wave properties of light. And so with that, it totally changes our understanding of how light progresses. What is light? How does light work? And so this was a major step forward right here, and was this phenomenal, huge deal. Okay, so with that, I'll go on and pause this little lecture, and we'll start the next one.